In 11 days, Comet 3I Atlas will vanish behind the Sun, exactly when it should reveal its true nature. The timing is surgical. A new moon just erased the night sky. 3 coronal mass ejections are hammering Earth's magnetosphere, and in less than 2 weeks every telescope on Earth will point uselessly at 965,000 miles of incandescent plasma, while this object performs what could be the most important maneuver in human history, completely hidden from view. Here's what we know before it disappeared. The James Webb Space Telescope found an 8.1 carbon dioxide to water ratio, 6 standard deviations above every comet ever measured. The Keck Observatory mapped nickel emissions that look more like industrial alloys than primordial ice. Mars spacecraft photographed sunward-biased outgassing that defies basic physics. The trajectory probability, 1 in 20,000. And if something wanted to break into orbit around our Sun right now, hidden behind our star would be the mathematically optimal moment to do it. The accumulated improbabilities have reached a point where dismissal requires more faith than consideration. Let me be clear about what's happening. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun at 136 astronomical units. This is the crucible where comets either prove their nature or reveal something else entirely. When a comet made of primordial ice and rock encounters this kind of heat, predictable things happen. Water sublimates into steam, frozen carbon dioxide turns directly to gas. Dust particles lift off the surface, carried by expanding vapor. The coma, that fuzzy envelope surrounding the nucleus, grows brighter and larger. The tail stretches millions of miles behind the comet, pushed by solar wind and radiation pressure. We've seen this dance countless times. We understand the choreography. But 3I Atlas has never followed the script. And now, just as solar heating should force it to reveal hidden volatiles, just as we should be learning the most about its true nature, it disappears into superior conjunction. The geometry is simple but frustrating. 3I Atlas approached the Sun from one direction, and Earth sits on the opposite side of our star. For several weeks, the Sun itself blocks our view. No telescope on Earth or in Earth orbit can see through 965,000 miles of incandescent plasma. We're in what astronomers call superior conjunction, and it couldn't have come at a worse time. Or perhaps, depending on your perspective, it came at exactly the right time. December will tell us if the same object emerges, but here's what we know happened before it vanished. Superior conjunction isn't unusual. It happens to planets, to spacecraft, to any object whose orbit takes it behind the Sun from our perspective. Mars goes through superior conjunction every 26 months. Venus experiences it every year and a half. We lose contact with our Mars rovers and orbiters for weeks at a time during these periods. We plan for it. We send commands in advance. We put systems into safe mode. We wait. It's inconvenient but predictable. What makes this different is the object in question and the timing of events surrounding its disappearance. Consider the sequence. 3I Atlas was discovered on July 1, 2025 by the Atlas Survey Telescope in Chile. From that moment, it became the focus of intense scrutiny. Initial observations suggested something unusual about its composition. Follow-up spectroscopy revealed emissions in ratios that didn't match anything in our solar system. The James Webb Space Telescope observed it in early August and found a coma dominated by carbon dioxide in an 8.1 ratio with water, the highest ever recorded in any comet, 6 standard deviations above the norm. Then came the trajectory analysis. Multiple groups calculated its orbit and realized it approached remarkably close to Venus, Mars and Jupiter with a cumulative probability of less than 0.05%. Its orbital plane tilted only 5°G from the ecliptic, another low probability configuration. Questions multiplied faster than answers, and now, at the moment of perihelion, when solar heating should force any hidden volatiles to reveal themselves, when the comet should be at its most active and most observable, it vanishes behind the Sun. Coincidence? Perhaps. The laws of celestial mechanics don't care about our curiosity. Orbits are what they are, determined by gravity and momentum, not by dramatic timing. 3I Atlas didn't choose to reach perihelion during superior conjunction. It simply followed the path carved by its velocity and the Sun's gravitational pull. But coincidences have a way of accumulating around this object, and some researchers are starting to wonder if that word still applies. There's another element to consider. one that adds strange synchronicity to the October timeline. On October 21st, just 8 days before 3i Atlas reached perihelion, Earth experienced a new moon. For those who don't follow lunar phases closely, a new moon occurs when the moon passes between Earth and the Sun, rendering it invisible to us. The side facing Earth is in shadow. The moon effectively disappears from the night sky. And on this particular new moon, something else happened. 3i Atlas reached what astronomers call superior conjunction with the Sun at nearly the same moment. The moon disappeared. The comet disappeared, both occulted by our star within hours of each other. The alignment occurred in the constellation Virgo, with the Sun, Moon and 3 Atlas forming a nearly perfect line stretching across the solar system. Astrologically minded observers have made much of this. I'm not an astrologer, but I can appreciate the poetry of the moment. A new beginning, a hidden visitor, a cosmic reset button, all occurring simultaneously. Some have suggested this represents a powerful energetic moment, a convergence of celestial forces that might influence events on Earth or reveal hidden truths about the comet. I'll leave such interpretations to those who find meaning in alignments. But I will note this. The timing struck even professional astronomers as noteworthy. When you spend your career analysing orbital mechanics and celestial events, you develop an intuition for what feels statistically normal and what doesn't. Multiple researchers have mentioned in private conversations and public talks that the October convergence felt unusual, not impossible, not even particularly improbable when you calculate the numbers, just unusual in a way that makes you pause and wonder if you're missing something. On August 6, 2025, the James Webb Space Telescope turned its instruments toward 3i Atlas. The observations took only a few hours, but the data they produced would fundamentally reshape our understanding of this comet. The spectrum-spanning wavelengths from 0.6 to 5.3 micrometers revealed a coma absolutely dominated by carbon dioxide. Not just rich in carbon dioxide, dominated. The team led by Martin Cordner at NASA's Goddard Space Flight Center analysed the emission lines and calculated the ratio of carbon dioxide to water in the coma. They found an 8.1 ratio. For every molecule of water sublimating from the nucleus, 8 molecules of carbon dioxide escaped. This isn't a minor deviation from the norm. This is a 6 sigma anomaly, meaning it lies 6 standard deviations above the trend for long-period and Jupiter family comets as a function of heliocentric distance. In statistical terms, 6 sigma means the probability of this occurring by random chance, assuming 3i Atlas is a normal comet, is less than 1 in a billion. You don't get 6 sigma deviations from random noise. You get them when something fundamental is different. To understand why this matters, we need to talk about comet composition. Most comets are dirty snowballs, mixtures of water ice, frozen gases like carbon monoxide and carbon dioxide, organic compounds, and silicate dust. The exact proportions vary, but water ice usually dominates. Water is abundant in the universe. It forms easily in cold environments. It's sticky, meaning it can trap other molecules and dust grains into a cohesive mass. When a comet approaches the Sun and begins to warm, the water ice sublimates first, creating the coma and releasing the dust and other volatiles embedded within it. Carbon dioxide ice has a lower sublimation temperature than water ice, so it starts out gassing farther from the Sun, but there's usually less of it. A typical comet might show a carbon dioxide to water ratio of 1:10 or 1.5 at most. Some comets are carbon dioxide rich, showing ratios approaching 1:1, but those are outliers, unusual objects that get studied carefully because they deviate from the standard model. 3i Atlas doesn't just deviate, it obliterates the standard model. 8.1 is off the charts. It's the highest carbon dioxide to water ratio ever measured in a comet. Where do you get so much carbon dioxide and so little water? The simplest explanation is formation location. In a protoplanetary disk, different molecules freeze out at different distances from the star depending on temperature. Close to the star, it's too hot for anything to condense. Farther out, you hit the water frost line, where temperatures drop below about 170 Kelvin, and water ice can form. Farther still, beyond about 3 or 4 astronomical units depending on the disk properties, you reach the carbon dioxide frost line, where CO2 freezes. Objects that form just beyond the carbon dioxide frost line could in theory be rich in carbon dioxide ice with less water, because the water mostly froze out closer in and the local material is dominated by the more volatile ices. This is a plausible scenario for 3I Atlas. If it formed far from its parent star in the cold outer regions of a protoplanetary disk, it would naturally be carbon dioxide rich. The composition would be a direct fingerprint of its birthplace, telling us that this comet comes from the deep freeze, the distant reaches where sunlight barely penetrates and temperatures hover just above absolute zero. But there's a complication. The carbon dioxide to water ratio in 3I Atlas is so extreme that it suggests not just formation beyond the carbon dioxide frost line, but something more. Maybe the comet formed in a region with unusually low water abundance to begin with. Maybe the disk was depleted in water, perhaps because it formed from gas that had already been processed in some way, stripped of its lighter molecules by radiation or winds. Or maybe the comet underwent some kind of evolutionary process after it formed, something that selectively removed water while leaving carbon dioxide behind. This is trickier to explain. Water and carbon dioxide have similar volatility, so a process that removes one should remove the other. Unless, and this is speculative, the comet has a layered structure. Perhaps the surface is water-poor and carbon dioxide-rich, a result of irradiation by cosmic rays over billions of years. Cosmic rays can break apart water molecules, liberating hydrogen which escapes into space, leaving behind oxygen that might recombine into other compounds or react with the dust grains. Over time, a surface layer could become depleted in water and enriched in more stable molecules like carbon dioxide. When the comet enters the inner solar system and starts sublimating, we see the composition of that processed surface layer, not the pristine interior. This would mean 3I Atlas is old, very old, possibly older than our solar system. Dynamical models of 3I Atlas's orbit, working backward from its current trajectory through the gravitational fields of the Milky Way, suggest the comet has been wandering interstellar space for at least 3 billion years, possibly as long as 14 billion years. The wide range comes from uncertainties in the galactic potential and the unknown history of gravitational encounters the comet experienced. But even the lower, estimate, 3 billion years, is ancient. The solar system itself is only 4.6 billion years old. If 3I Atlas is 3 billion years old, it formed during an earlier era of the Milky Way, when star formation rates were higher and the chemical composition of the galaxy was different. A comet formed around such a star would have a different starting composition than a comet formed in our solar system. Lower metallicity, fewer heavy elements, different abundance ratios. The extreme carbon dioxide dominance could reflect that ancient alien environment. The JWST observations also detected water, carbon monoxide and carbonyl sulfide in the coma, along with water ice grains and dust. So it's not that water is absent, it's present, just overwhelmed by the carbon dioxide. The carbon monoxide to water ratio, at about 1.41, is also elevated but less dramatically. The carbonyl sulfide, OCS, is a trace component, interesting because it's relatively rare in solar system comets, and its presence hints at sulfur chemistry that we don't fully understand. The isotopic composition of the carbon dioxide provided another clue. JWST detected both carbon-12 and carbon-13 in the CO2 molecules. While the exact ratio is difficult to quantify due to overlapping spectral features, the preliminary analysis suggests it's broadly similar to the ratio found on Earth and in solar system comets. This is significant because it means the carbon in 3I Atlas came from similar nucleosynthetic processes as the carbon in our own neighbourhood. It rules out some of the more exotic formation scenarios, like condensation from molecular clouds with very unusual isotopic signatures. The carbon in this comet is normal carbon, just arranged in an unusual molecular form. NASA's SPHEREX mission independently confirmed the carbon dioxide dominance in observations made between August 7th and 15th. SPHEREX lacks the sensitivity to detect water vapour, but it clearly saw the carbon dioxide emissions and measured a mass loss rate of about 70 kilograms per second. For comparison, typical comets at similar distances from the Sun might lose a few tens of kilograms per second of water. 3I Atlas is losing 70 kilograms of carbon dioxide alone, with much less water. The activity level is high, driven by the readily sublimating carbon dioxide ice, which means the comet's nucleus is shedding mass quickly. Over the course of its passage through the inner solar system, it might lose a significant fraction of its total mass, perhaps a few million tons of material. This isn't unusual for comets, but it does raise the question, how many prior passages has this comet made through other stellar systems? If it's been wandering for billions of years, has it encountered other stars, undergone other perihelion passages that stripped away outer layers? Is what we're seeing now the core of a once much larger object, a relic worn down by eons of exposure to stellar radiation? The answers remain elusive, but the carbon dioxide dominance offers a hint. This is not a fresh, pristine comet just ejected from its home system. This is something that has survived a long journey, and it carries the scars of that journey in its chemistry. Then there's the nickel problem. The Keck Observatory in Hawaii, using the Keck Cosmic Web Imager, observed 3I Atlas on August 24th at wavelengths specifically chosen to reveal two molecules, nickel and cyanide. These aren't random selections. Cyanide in the form of CN radicals is common in comets, a signature of organic chemistry frozen into the ice during the comet's formation. Nickel, on the other hand, is unusual. Most comets emit very little atomic nickel. When they do, it's typically accompanied by roughly equivalent amounts of iron, reflecting the cosmic abundance ratios you'd expect from a chunk of primordial solar system material. But earlier observations of 3I Atlas had hinted at something strange. Strong nickel emissions with far less iron than expected. The Keck team wanted to map those emissions in detail, to see how the nickel and cyanide distributed themselves around the nucleus, and to understand what that distribution might tell us about the comet's structure and activity. The results were striking. The processed images showed a coma roughly 6,000 kilometers across at the wavelengths observed, with a bright central concentration where the nucleus sits buried beneath layers of gas and dust. But the coma wasn't symmetric. The nickel emissions formed a relatively compact envelope around the nucleus, concentrated but not perfectly round. The cyanide emissions spread much wider, extending significantly farther from the nucleus in all directions. This difference in spatial extent makes sense if you think about the physics. Cyanide molecules are lighter and more easily accelerated by solar radiation pressure and the expanding gas from the comet's sublimating ices. Nickel atoms are heavier, so they don't travel as far before they either ionize and get swept away by the solar wind or simply fall back toward the nucleus. The size difference between the two envelopes isn't surprising. What surprised observers was the direction. Both the nickel and cyanide showed a bias toward the sunward direction. Remember, comets typically push material away from the sun, forming tails that point in the anti-solar direction. But 3I Atlas, even back in August when it was still more than 3 astronomical units from the sun, showed enhanced outgassing in the direction of the star. The Keck images made this asymmetry visually obvious. The coma wasn't evenly distributed, it bulged sunward. And this pattern, first noticed in August, persisted through the October observations from Mars' orbit. It's a consistent feature, not a measurement artifact or a one-time glitch. The comet really does behave this way. The explanation? Slow rotation or tidal locking. If the nucleus doesn't rotate rapidly, if it's tidally locked or tumbling slowly, the day side could remain constantly heated while the night side stays cold and inactive. All the sublimation would occur on the sunward hemisphere, pushing material outward in that direction before the solar wind catches it and sweeps it back into a more traditional tail configuration. It's a reasonable model, it fits the data, but it also requires specific conditions, a slowly rotating nucleus, which is somewhat unusual for objects that have spent billions of years tumbling through space, subjected to every gravitational nudge and collision imaginable. Objects tend to spin. 3I Atlas apparently doesn't spin much, or it's hiding something. Now let's talk about the nickel itself. Spectroscopic observations from multiple observatories, including the Very Large Telescope in Chile, have confirmed strong nickel emissions with far less iron than expected. Some reports suggested iron was essentially absent, though that's probably an overstatement. More likely, the iron-to-nickel ratio is significantly lower than normal, perhaps approaching 1.1, or even showing a nickel excess. This is weird. In nature, nickel concentrates in certain types of meteorites, particularly iron meteorites, and the metallic cores of differentiated asteroids. When a large body forms and undergoes differentiation, heavy elements like iron and nickel sink toward the center, forming a metallic core. If that body later gets disrupted by a collision, Fragments of the core can survive as iron-nickel meteorites. These meteorites have much higher nickel content than average rocky material, sometimes reaching 20 or 30% nickel by mass. But they still contain more iron than nickel. You don't get pure nickel or nickel-dominated materials in natural planetary processes, at least not that we've seen before. The other place you get concentrated nickel is in human industrial processes. Nickel-steel alloys, stainless steel, various nickel-based superalloys used in aerospace and high-temperature applications. These are engineered materials, not natural minerals. And while nobody seriously suggests 3i Atlas is made of stainless steel, the comparison has been raised, sometimes as a joke, sometimes as a pointed question. What natural process creates a comet nucleus with anomalous nickel emissions? One possibility is that 3i Atlas formed in a protoplanetary disk with unusual chemical abundances. If the star system where it originated had a different composition than our Sun, if it was enriched in certain elements due to the history of supernova enrichment in that region of the galaxy, then the comet could inherit those unusual abundances. This is a perfectly plausible explanation. The Milky Way is not chemically uniform. Different regions, different stellar populations have different mixes of elements. A comet from the galactic thick disk, an older stellar population with lower metallicity, could have a composition unlike anything we see in our own solar system. The problem with this explanation is that it requires not just different abundances, but specifically a nickel enrichment, which is harder to justify on nucleosynthetic grounds. Nickel comes primarily from supernova explosions, just like iron. They form together in the cores of massive stars and get ejected together when those stars die. Getting a lot of nickel without a lot of iron means you need some kind of selective process, something that separates these elements after they're created, and that's not straightforward. Another possibility involves the comet's thermal history. If 3i Atlas passed close to a star at some point in its past, if it underwent heating that selectively vaporized certain elements while leaving others behind, you could potentially fractionate the composition. Iron has a lower boiling point than nickel, so in theory you could boil off iron preferentially, leaving a nickel-rich residue. But this requires extreme heating, temperatures high enough to vaporize metals, and if the comet underwent that kind of heating, it probably wouldn't retain much ice. It would be a dead, inactive rock, not an outgassing comet. The observations don't support that scenario. 3i Atlas is clearly active, clearly icy, clearly sublimating volatiles like carbon dioxide and cyanide. It hasn't been baked into a metallic cinder. A third possibility, and this is where things get speculative, is that the nickel emissions come not from the bulk composition of the nucleus, but from a surface layer or specific active regions enriched in nickel-bearing minerals. Maybe the comet nucleus is heterogeneous, with patches of different composition. Maybe one region happens to contain nickel sulfides or nickel carbonates that sublimate more readily than the surrounding material, creating localized emission hotspots that dominate the observed spectrum. This would explain the asymmetry seen in the Keck images. If the nickel comes from a specific active vent or jet on the nucleus, and that vent happens to face sunward, you'd see exactly the pattern observed. This is actually a pretty reasonable model. Comet nuclei are messy, heterogeneous objects, not uniform ice balls. They can have distinct layers, buried pockets of volatiles, regions with different dust-to-ice ratios. A nickel-rich patch isn't beyond the realm of possibility. But again, it raises the question of origin. How does a comet end up with a nickel-rich patch? What's the formation or evolutionary process that creates such a feature? These aren't easy questions, and the answers probably require more data than we currently have. Avi Loeb has argued that the nickel anomaly, combined with the trajectory anomaly and the other unusual features, pushes the cumulative probability of 3i Atlas being a natural comet low enough that we should take the artificial hypothesis seriously. He doesn't claim it's definitely artificial. He says the probability is significant, maybe 30 or 40%. Enough to warrant careful scrutiny and open-minded investigation. Most of his colleagues disagree with that assessment. They point out that interstellar objects are, by definition, samples of one. We have no statistical baseline for what's normal or unusual among comets from other star systems. Oumuamua was weird too. It showed non-gravitational acceleration without visible outgassing, had an elongated shape, tumbled in a complex rotation state, but subsequent analysis suggested it could be explained as a hydrogen iceberg, a comet made primarily of frozen hydrogen that sublimated without producing a visible coma. Weird, yes, but ultimately natural. 2I Borisov looked much more normal, a fairly typical comet with a composition similar to solar system comets. 3I Atlas falls somewhere in between, more active than Oumuamua, more chemically unusual than Borisov. The sample size of 3 is too small to draw firm conclusions. We need more interstellar visitors. We need to see if they're all weird in different ways, or if patterns emerge that point to common formation processes. And this is where the Vera Rubin Observatory becomes critical. June 23, 2025. The Vera Rubin Observatory released its first images to the public, and the astronomical community collectively gasped. The images were stunning, not because they showed objects never before seen, but because of the sheer scale and detail captured in such a short time. A mosaic of the Trifid and Lagoon Nebula, compiled from 678 separate images taken over just 7 hours, revealed clouds of gas and dust in exquisite detail. Faint structures invisible to smaller telescopes suddenly rendered in vivid clarity. A video panning across a tiny fraction of the sky showed approximately 10 million galaxies, each one an island universe containing billions of stars. And that was just 0.05% of what Rubin will observe over its 10-year mission. The numbers were staggering. In roughly 10 hours of commissioning observations, Rubin discovered 2,040 previously unknown asteroids, including 7 near-Earth asteroids that posed no threat but had gone unnoticed by every other survey. Annually, all other ground and space-based observatories combined discover about 20,000 asteroids. Rubin, in its first day of serious work, found 10% of that annual total. This isn't an incremental improvement over existing capabilities. This is a revolution. The Rubin Observatory sits atop Cerro Pachon in Chile, a 2,700-metre peak in the Andes chosen for its clear, dark skies and stable atmospheric conditions. The observatory houses the Simony Survey Telescope, an 8.4-metre instrument with an unusual design optimised for wide-field imaging. Unlike traditional telescopes that focus on small patches of sky at high magnification, the Simony telescope captures enormous swaths in a single exposure, 7 full moons wide with a field of view covering nearly 10 square degrees. This is made possible by the largest digital camera ever built for astronomy, the LSST camera. A behemoth weighing 3 tons and containing 3.2 gigapixels spread across an array of charge-coupled devices cooled to 100 Leyland. Each image from this camera is so detailed, it would require over 400 ultra-high-definition television screens to display at full resolution. And the telescope takes these images constantly, night after night, mapping the entire visible southern sky every 3 to 4 days. Over the course of a decade, Rubin will observe each patch of sky hundreds of times, creating a time-lapse movie of the universe in unprecedented depth and cadence. For interstellar object detection, Rubin is a game-changer. The problem with finding interstellar visitors has always been speed and rarity. These objects move fast, often tens of kilometers per second relative to the solar system, and they're faint, reflecting very little sunlight because they're small and dark and far away. By the time you discover one, calculate its orbit, and realize it's interstellar, it might already be leaving, shooting past the sun and back into the void before you can study it properly. This happened with Oumuamua. By the time astronomers recognized it as interstellar, it was too faint and too distant for detailed observations. 2I Borisov was luckier, discovered farther out and tracked for months, but still the observation window was limited. 3I Atlas was discovered relatively late in its approach, giving us only a few months to prepare campaigns and coordinate observations before perihelion. We need earlier detection. We need to find interstellar objects when they're still far from the sun, when we have time to plan, to mobilize resources, to perhaps even send a spacecraft if the object is interesting enough and the trajectory favorable. Rubin will provide that early detection. The observatory's survey strategy, called the Legacy Survey of Space and Time, or LSST, involves repeated observations of the same regions of sky separated by days or hours. This allows Rubin to detect anything that moves or changes: asteroids, comets, variable stars, supernovae, transient events of all kinds. Software algorithms compare each new image to previous images of the same region, identifying objects that have shifted position or altered brightness. For solar system bodies, this motion detection is straightforward. Asteroids and comets move against the background stars in predictable ways, and their angular motion across the sky tells you roughly how far away they are and how fast they're travelling. Interstellar objects move differently. They come in on hyperbolic trajectories with velocities high enough to escape the sun's gravity, and their motion across the sky can be faster than typical solar system objects. This makes them harder to detect with traditional surveys that assume objects move slowly and follow predictable orbits. But Rubin's cadence and coverage are designed to catch these fast movers. The machine learning algorithms being developed specifically for LSST data include classifiers trained to recognize interstellar object candidates based on their motion characteristics, distinguishing them from the thousands of asteroids and comets that clutter the inner solar system. Estimates vary, but most models predict Rubin will discover between 1 and 70 interstellar objects per year once it reaches full operational capacity. The wide range reflects uncertainties in the population density of these objects in nearby interstellar space. We know Oumuamua was discovered, and from that single detection we can infer a rough density, about 0.1 object per cubic astronomical unit at any given time. But that number is highly uncertain. It could be 10 times higher or 10 times lower, and we wouldn't know until we get more detections. If the density is on the high end, Rubin could find dozens of interstellar visitors every year. If it's on the low end, we might see only a handful per decade. Either way, within a few years we'll have a real sample, not 3 objects, but 30 or 300. Enough to start doing statistics. Enough to understand the range of compositions and trajectories and properties these visitors exhibit. We'll learn what's common and what's rare. We'll learn if 3i Atlas is an outlier or representative of a significant population. And we'll have opportunities, many opportunities, to study interstellar objects in detail, to launch dedicated missions, to perhaps even rendezvous with one and bring samples back to Earth. The detection of 3i Atlas itself provides a tantalizing preview of Rubin's capabilities. Although the official discovery came from the Atlas survey on July 1st, Rubin had actually imaged the comet 10 days earlier, on June 21st, during its commissioning phase. The images were archived but not immediately analysed because the observatory was still calibrating its systems and testing its data pipelines. When the Atlas discovery was announced, Rubin's team went back through their archives and found the comet sitting right there in their data, a faint smudge moving slowly against the starfield. This pre-discovery detection is significant because it shows Rubin can find interstellar objects even before they're officially recognised, even when they're still faint and far from the Sun. Once the observatory is fully operational and the automated detection algorithms are running in real time, such objects will be flagged immediately, within hours of observation, giving the astronomical community maximum time to respond. This could be the difference between a brief glimpse and a thorough investigation, between missing critical data and capturing a complete portrait of an interstellar visitor. The debate over 3i Atlas has split the astronomical community in ways that few objects have managed to do. On one side, you have researchers like Avi Loeb, the Harvard astrophysicist who has never been shy about proposing unconventional ideas, arguing that the cumulative evidence warrants serious consideration of the artificial hypothesis. On the other side, you have the majority of professional astronomers who insist that while 3i Atlas is unusual, it remains within the bounds of natural phenomena and doesn't require invoking extraterrestrial technology. The divide isn't just about interpreting data. It's about how science should approach extraordinary claims, about the balance between open-minded inquiry and skeptical rigour, about what counts as evidence and what counts as speculation, and it has played out very publicly in academic papers, blog posts, social media threads, and conference presentations, making 3i Atlas one of the most polarizing objects in recent astronomical history. Avi Loeb's position is nuanced, at least in his own telling. He doesn't claim 3i Atlas is definitely artificial. He says the probability is significant, somewhere around 30 to 40%, based on his assessment of the various anomalies, and that this probability is high enough to justify treating the artificial hypothesis as a serious scientific possibility, rather than a fringe idea to be dismissed out of hand. His argument rests on cumulative improbabilities, the 5-degree ecliptic alignment with 0.2% odds, the triple planetary close approach with 0.0% odds, the 8.1 carbon dioxide to water ratio that sits 6 sigma above the norm, the nickel emissions without corresponding iron, the sunward biased outgassing. Any one of these features, taken alone, could be explained as a rare but natural occurrence. But when you multiply the probabilities, when you stack low odds on top of low odds, the cumulative likelihood of all these features appearing together in a natural object becomes vanishingly small. At some point, Loeb argues, you have to consider the alternative explanation, that these features are not coincidences but design choices, indicators of intelligence and engineering rather than random cosmic accidents. The mainstream counterargument focuses on sample size and the problem of post hoc reasoning. With only 3 confirmed interstellar objects, we have no baseline for what's normal. We don't know the typical range of trajectories, compositions, or behaviors for objects from other star systems. Maybe 5-degree inclinations are common because of some dynamical pathway we haven't yet identified. Maybe carbon dioxide-rich comets are abundant in the thick disk population, reflecting different formation conditions billions of years ago. Maybe nickel emissions without iron are a signature of specific mineral phases that we rarely see in solar system comets, but are common elsewhere. Until we have a larger sample, we cannot judge what's anomalous and what's simply unfamiliar. The post hoc reasoning problem is equally important. If you look at any object with enough scrutiny, you'll find features that seem unusual or improbable. The human brain is wired to see patterns, to find meaning in randomness, to construct narratives that explain coincidences. 3i Atlas has received intense scrutiny precisely because it's interstellar and, therefore, interesting. If we apply the same level of analysis to a random solar system comet, we'd probably find comparable anomalies, unusual chemical ratios, unlikely trajectory alignments that could be spun into mysterious stories. The difference is that nobody bothers to look that closely at ordinary comets. The anomalies of 3i Atlas may simply reflect observational bias. We're looking harder, so we're finding more things.